We often frame the environmental crisis as a product of the last few decades, a sudden deviation from a natural baseline. However, the data suggests a different narrative. We are a terraforming species by nature, not just by accident. This presentation traces the history of humanity's planetary impact, identifying it as a continuous transition from ancient, regional footprints to a modern, global transformation. As we observe the nightlights in this visualization, we are seeing the physical manifestation of energy consumption that distinguishes the Anthropocene. But this light is merely the final signal of a process that began much earlier. To understand the scale of our current epoch, we must first look back to the Pleistocene, where our capacity to alter the biophysical environment first emerged, not through industry, but through fire and predation. Our analysis of anthropogenic impact begins approximately 800,000 years ago with the controlled use of fire by hominins. This was our first tool for landscape modification. Repeated deliberate burning, particularly in drier environments, aggregated over millennia to alter vegetation patterns significantly. Following this, we observed the late Pleistocene extinctions. While climate change drove vegetation shifts that fragmented habitats, the quote, overkill hypothesis remains a critical variable. Archaeological evidence confirms cooperative hunting of megafauna, animals exceeding 40 kilograms, for high-energy fat and protein. This pressure contributed to, quote, defaunation, the disappearance of ecosystem engineers like mammoths and woolly rhinos. Thus, even as foragers, humans were already acting as a selective force, thinning the biosphere's megafaunal density long before the first seed was sown. The dawn of cultivation, approximately 10,000 years ago, marked the transition from biological predation to geological resurfacing. The conversion of grasslands, forests, and wetlands into cropland initiated the first substantial land use changes. We must consider the, quote, early Anthropocene hypothesis proposed by Rudiman, which argues that early cultivators began altering the global climate as early as 8,000 years ago. Carbon dioxide emissions from deforestation and methane from rice cultivation and livestock may have produced a warming effect sufficient to cancel a natural cooling trend of the era. While early populations were small, their per capita land requirements were high, making this period the true start of direct, intentional, and climatically significant land use change. Energy density dictates landscape integrity. Pre-modern societies, lacking fossil fuels, relied on wood for heating, construction, and, critically, metallurgy. The production of iron was incredibly wood-intensive. Early smelting required up to 80 kilograms of wood to produce the charcoal necessary for a single kilogram of hot metal. The visual evidence in Central Europe is striking. Forest cover plummeted from approximately 70% in 900 CE to a mere 25% by 1900. Similarly, between 1700 and 1900, China lost no less than 90 million hectares of forest, nearly 40% of its remaining cover. This great clearing illustrates that extensive environmental disfigurement is not solely a product of the 20th century, but a prerequisite for any civilization transitioning through the Metal Ages. By 1800, after millennia of fire, hunting, and agricultural expansion, the human imprint was regionally severe but globally contained. As the data indicates, human activity had altered significant portions of the Mediterranean and China, yet from a planetary perspective, the transformation was limited. At their post-glacial peak, primary forests covered roughly 40% of ice-free land. By 1800, this area had been reduced by no more than 10%. This is a crucial threshold in our timeline. It represents the world on the cusp of a radical phase shift, a biosphere that had absorbed human activity without yet succumbing to it. This relative stability was about to be shattered by the unlocking of fossil carbon. The last 2 centuries have witnessed an unprecedented acceleration that defies linear historical comparison. This graph, often termed the Great Acceleration, tracks the synchronized explosion of population, cropland, atmospheric CO2, and primary energy use. We have altered 2/3 of the planet's ice-free land. The grand total of land affected by human action, including agriculture, infrastructure, and mining, is now approximately 9 billion hectares. This accounts for roughly 67% of all non-glaciated land. We have effectively transitioned from being a species inhabiting the planet to an unrivaled terraforming agent, with energy consumption and resource extraction rates that dwarf geological background processes. When we visualize human impact, we often think of concrete cities. However, the data reveals that cropland and pastures are the planet's most extensive altered ecosystems. Since 1800, we have seen a massive expansion. Cropland doubled in the 19th century and grew another 80% in the 20th to surpass 1.5 billion hectares. Pastures expanded even more aggressively, growing 2.7-fold to over 3.4 billion hectares. In stark contrast, urban areas, our paved planet, account for less than 1% of the world's non-glaciated land. While cities drive resource consumption, it is the sprawling footprint of agriculture that physically displaces the biosphere. We observe a phenomenon known as the, quote, forest transition. In affluent nations like France, Italy, and the US, forest cover has expanded significantly since the mid-20th century. This, quote, great regrowth is driven by the abandonment of marginal farmland and the substitution of fossil fuels for wood fuel. However, this local recovery is offset by the great clearing in the tropics. Between 1990 and 2015, Brazil led the world in primary forest loss, erasing 15.5 million hectares. Haiti provides a tragic extreme, with primary forest reduced to 0.32%. While the net global deforestation rate has halved recently due to reforestation, the loss of biodiverse, primary tropical forest continues at an unacceptably high rate, effectively exporting environmental degradation to the equator. The shift in biological mass is staggering. By the year 2000, the biomass of domesticated mammals weighed in at approximately 600 million tons, 25 times greater than that of all wild terrestrial mammals combined. We have reversed the normal trophic order. Humans and our livestock now overwhelmingly dominate the planet's vertebrate biomass. This industrial harvesting extends to the oceans. Industrial fishing now covers more than 55% of the ocean's surface, an area 4 times larger than all terrestrial agriculture. By 2009, 87% of global fish stocks were fully exploited or overexploited. We are witnessing the, quote, emptying ocean and a land surface converted into a factory for protein production. Industrialization birthed new forms of widespread pollution. Some, like acid deposition, acid rain in the 1970s and 80s, represent success stories. Technological interventions largely controlled these emissions, turning them into a footnote of history. However, we have entered the, quote, plastic age. Unlike sulfur, plastics are persistent. Cumulative production reached 7.8 gigatons by 2015. The statistic is damning. Of all plastic waste ever generated, 79% has accumulated in landfills or the environment. In 2010 alone, up to 12.7 million tons entered the ocean. This is not just litter. It is a new geological stratum of synthetic material that will persist for centuries. Human activity now dominates the global nitrogen cycle. Through the Haber-Bosch process, legume cultivation, and fossil fuel combustion, we fix approximately 210 million tons of nitrogen per year. This mass is significantly larger than the total pre-modern mobilization from all natural sources combined. We have effectively doubled the planet's flow of reactive nitrogen. The consequence is the, quote, nitrogen cascade. Excess nutrients flow into coastal waters, driving eutrophication and creating over 500 feet dead zones worldwide. Similarly, we mobilize phosphorus at 5 times the pre-modern rate. We are not just living on the planet, we are actively altering its baseline hydrochemical stoichiometry. Stratigraphers argue that the mid-20th century marks the boundary of the Anthropocene, a new geological epoch where human activity is the dominant terrestrial force. We move sediment an order of magnitude faster than natural erosion. However, a note of humility is required. While we have defaunated and transformed the surface, the ultimate controls of the planet, plate tectonics, solar output, and orbital mechanics, remain completely beyond our reach. We can destroy the environment that sustains us, but we cannot control the megaforces that shape the Earth's crust or its place in the solar system. We are powerful terraformers, but we are not planetary architects. The human footprint is a cumulative measure of infrastructure, agriculture, and population density. The data reveals that 75% of the planet's land surface now experiences measurable human pressure. Only 23% of land, mostly in hostile environments like the tundra or deep deserts, can be classified as wilderness. However, there is a sign of relative decoupling. Between 1993 and 2009, while the global economy expanded by 153% and population by 23%, the human footprint grew by only 9%. This suggests we are becoming more efficient at extracting value per unit of land, yet the absolute pressure continues to rise. We are doing more with less, but we are doing so much more that the wilderness continues to shrink. This is arguably the most consequential graphic of the presentation. For 800,000 years, atmospheric CO2 fluctuated within a narrow natural band. For the last millennium before industrialization, it was stable at roughly 280 parts per million. We have now forced this concentration to over 414 ppm, a vertical spike in the geological record. Since the mid-19th century, the radiative forcing attributable to this CO2 is about 2 watts per square meter. The physics are undeniable. We have raised the average global temperature by 1 degree Celsius, and we are on a trajectory for 1.5 degrees Celsius between 2030 and 2052. We are not just altering the land, we are changing the thermal operating parameters of the entire biosphere. We navigate a world of our own making, defined as much by what is missing as what is present. Since the dawn of agriculture, we have reduced the total standing stock of terrestrial phytomass, the sheer mass of plants on Earth, by nearly 40%, from 1,000 gigatons of carbon to roughly 650 gigatons. We have reversed the trophic order, replaced the wild with the domestic, and altered the atmosphere. The challenge of the past was expanding our agricultural and economic foundations. The challenge ahead is vastly more complex. We must displace 10 billion tons of fossil carbon annually, while sustaining a population of 10 billion people on a planet we have fundamentally and irrevocably altered.